Hello again. We are now doing the fourth lecture of fourth week. As I said, this will be the last week where we look at graph coverage criteria. We saw graph coverage criteria on code. Last two lectures I told you how to apply graph coverage criteria for integration testing that deals with testing for design, that is interaction and interfaces between modules. Now we'll move on to requirements on design. So what we will see in this module and in the next module is somewhere between design and specifications, and see how graph criteria apply to test these also. So we will understand what specifications are. The focus of this lecture will be specifications that actually talk about design itself. So I'll explain to you through examples what it means to write specifications that talk about design, because there are several specifications that we need to write along with the design to ensure that things are working correct, even though these specifications may not explicitly map to the requirements of a software. So today we will deal with those kind of specifications, and in the next lecture I will introduce you to finite state machines, finite state automata, which are a popular model to write requirements, and then we will see how graph coverage criteria work on them. What is a design specification? So as I told you, design describes what are the modules in the software, how a software is broken up into its components, and how they interact with each other and what happens. The design specification talks about what are the requirements or constraints that need to be satisfied by the design that is being written and baseline to make the design correct. Not all design specifications are derived directly from the requirements of software. Some of them are extra specifications written to ensure that the design is indeed correct. So design specification can be thought of as a part of the model, design model corresponding to the implementation. While we do graph-based testing, we will consider two types of design specifications. What I'll do in today's lecture would be what is called sequencing constraints, which are constraints on methods and functions that come in the design, on modules that come in the design. Not all sequencing constraints can be used to write all kinds of design specifications. So certain things that cannot be used, we will look at finite state machines that describe state behavior. That we will do in the next lecture. So what is a sequencing constraint? Before I introduce you to what is a sequencing constraint, I would like to begin with a small example. Let's say this is just another abstract snippet of some design. It says that there are two methods here. Both the methods deal with a queue data type. You know what a queue data type is, right? A queue is a first in first out list or an array of elements. So what are the typical operations that come with a queue? The typical operations that come with a queue are enqueue and dequeue. Enqueue inserts an element into the queue. Dequeue removes an element that is already present at the other end of the queue, right? So there are these two methods. One is in dequeue, which is remove the element from the queue and assign it to an integer variable. The other is insert an integer into a queue, right? And I haven't really given the code for these methods, but if you see, there are two comments that are written here. For dequeue, there is a comment which is named pre, which says at least one element must be on the queue, right? So you can read this as it is a precondition which says that there must be at least one element in the queue. Why is this thought of as a precondition? Let's say the queue was empty. Then how do I dequeue anything? I will not be able to dequeue, right? Dequeue will give me an error. So to be able to dequeue, I need at least one element in the queue. So I state it like a precondition. And if you read what is written in enqueue, I have written again as a comment a post condition which says that E is at the end of the queue. So this is which basically says that the queue is like a FIFO data structure, first in first out data structure. So when I insert an element in the queue, it goes to the end of the queue, and for me to remove an element from the queue, the precondition is that there must be at least one element in the queue. So these can be thought of as basic constraints that tell you what methods enqueue NQ and DQ should satisfy. The methods NQ and DQ could be used as a part of a mainstream functionality that is meant to cater to a particular requirement of a software. But wherever they are used, these preconditions and postconditions basically say what will happen or what should happen when they are used. Precondition for DQ says that the queue should not be empty, so there should have been at least one NQ operation without another DQ operation before the current DQ operation. And the postcondition for NQ says that after an element is inserted into the queue, it goes to the end of the queue. So these are what are called sequencing constraints. So what is a sequencing constraints? These can be thought of as rules that impose some constraints in the order in which the methods in a particular piece of code can be called. Like for example, for me to be able to do DQ, I should have done at least one NQ in the past. So these can be written as preconditions, postconditions, asserts, or any other way of writing it, and they are requirements that we impose on the design of the software, right? Another thing that I told you that is to be noted is that these are typically not given as a part of the specification document or as a part of the requirement document. These are written along with design, typically by designers, to ensure that their design works correctly, in the sense of it is necessary that these constraints are satisfied for the design to be able to meet its expected functionality. Suppose they are typically not given, then the onus is on the tester to be able to derive them and test them. So this is the queue example that we saw of a simple sequencing constraint on a queue, which basically says that NQ must be called before a DQ. If that's not the case, then the queue could be empty because it begins with an empty queue and there is nothing to DQ from, right? So I don't want to keep trying to DQ from an empty queue. So I insist that there must be at least one NQ operation before a DQ operation. Here in this example, such a sequencing constraint is given implicitly as pre and post conditions. In fact, you can write several such other sequencing constraints for the queue example itself. Another simple sequencing constraint is something like this. It says that there must be at least as many NQ calls as there are DQ calls. Why do we need this? Let's say I have a queue. The queue contains at any point in time, at some point in time, let's say it contains 3 elements. So what can I do? I can do continuously 3 DQs. So how did the 3 elements come into the queue? There must have been 3 NQ operations in the beginning, before the 3 DQ operations. It can never be the case that there were only 2 NQ operations. If there were only 2 NQ operations in this queue, the queue cannot have 3 elements, right? Assuming that the queue was empty to start with. So what it says is that to be able to DQ, I should have NQ'd an element in the past. So at any point in time, the following holds as an invariant. The number of NQ operations should be greater than or equal to the number of DQ operations. So if you see, the word number matters here. We're talking about the number of NQ operations and the number of DQ operations. Whenever I'm counting the number of operations related to a particular piece of software execution, I typically cannot write it as a simple assertion or a sequencing constraint. I need what are called state-based models for that. We won't look at state-based models in this lecture. That will be the focus of next lecture. But what I wanted to tell you as a part of this lecture is that when I take a queue example or any other kind of example, which is meant to be like a data structure serving as a part of a method, I could write constraints which talk about how the data structure should work correctly. Such constraints are called sequencing constraints. Some sequencing constraints can be written as simple invariants, like we saw here. NQ must be called before a DQ. Some sequencing constraints need to deal with history or memory or number, and they need state machines to be able to write them, which we will see in the next lecture. So as I told you, sequencing constraints typically are not explicitly given. Say they always have to be written by the designer, and it could very well be the case that the designers miswriting them. If the designers miswriting them, then the onus is on the tester to be able to identify, write them, and test for all these sequencing constraints to be met. Like interfaces, when you go into integration testing, absence of correct sequencing constraints or the software not adequately tested for correct sequencing constraints is meant to lead to a rich source of errors, and the onus is on testers to be able to identify and eliminate these errors during integration testing. So we'll see how to test for sequencing constraints through an example. Consider a class called FileADT. ADT stands for Abstract Data Type. This is a class that encapsulates operations on a file. That file has some kind of data. What is the typical bare minimum set of operations that you would do on a file? You could open a file, which is done through this command, open a file name with the name fname. So this is a method open which lets you to open a file name with the name fname, and once a file is opened you could close it. I have not given an argument as the name of the file here just for convenience sake, but you could as well write close a string followed by file name so that you know which file to close. Because I have not written an argument for close here, I assume through the examples that we look at that I am working with only one file at a time. Suppose it happens to be the case that you're working with more than one file, you need to give close operations for that file name also. And once a file is open, before being closed, you would want to work with the file. You could read data from the file or you could write onto a file. So here is a method that writes onto a file. So this method writes a line of text called text line, which is a string to the file. So there is a class file abstract data type, in short FileADT, which encapsulates three methods: open file, close file, and write data to a file. So if you think about sequencing constraints for any code that uses these methods, so there is a code that deals with some file operations, and in the process of dealing with those file operations it uses methods that are available as a part of this class. What would be sequencing constraints that you will write for such kind of code? The obvious kind of sequencing constraints are as follows. A file must be opened before you can write onto it. An open file must be closed before you finish operations. Better not leave it open. A write may not be executed after a close unless there is an open in between. So what it says is, suppose you open a file and then you write and then you close the file and then you have to open it once again to be able to write. Right? So once you close the file, you cannot write onto it without opening it again. And then the fourth sequencing constraint says that a write should be executed before every close. So what does the fourth one say? Fourth one says write should be executed before every close. So suppose this is violated. Then what will happen? Then it means that a piece of software is trying to do some dummy operations on a file. It could just open a file, close a file, open a file, close a file without doing anything. It doesn't read from a file. It doesn't write onto a file. So it is just keeping itself busy but doing nothing. So we would want to prevent such things. So we say that once a file is open, do something with it. Do something like a write with it before you close it. The other thing that you must notice in this slide is that I have put words like must in the first two constraints and the word should in the fourth constraint in italic font. What do we mean by that? Typically, when we write requirements or specifications or constraints, you will encounter these words a lot when you write requirements in English. May, must, shall, should. And what do they usually mean? Usually the presence of a word must means that if that requirement or constraint is violated, then there is a fault for sure. And the word like should be interpreted as if that requirement or constraint is violated, then there might be a fault. So it is clear even for this example that something like that holds, right? Suppose let's say the second requirement, consider the second constraint. It says openF must be executed before every close. So suppose this is violated, which means what, somebody has tried to close a file that wasn't even open. That's not possible, so it will definitely result in a fault, and it's a must sequencing constraint. Look at the fourth sequencing constraint. It has the word should. Should means that somebody is trying to write onto a file. Somebody's opened the file and closed the file without writing onto it. It's harmless in the sense that it doesn't really cause a serious fault, but it is useless also. So a requirement with a should may or may not result in a false. So we have to be careful about when we use must and should kind of requirements. These are typically done by requirement engineers who write software requirement or by architects who specify the design. Right now I have a class that contains these three methods. These are the sequencing constraints on the method. Now what I want to do is the following. Consider a piece of code that uses methods from this class. Then that piece of code should satisfy all the sequencing constraints that we have written, right? Which means it must open a file before it writes onto it and promptly close a file, and it must not ideally open and close a file without doing a write operation in between. Those are the kind of things that we do. So what we do is that we consider the code that uses the methods from this class. You consider the control flow graph of that code. Then what will be your test requirement and test paths? They would be test paths in the control flow graph that check if any of these constraints are violated. Typically, for sequencing constraints, there are two ways of doing it. You can try to violate the sequencing constraints in a static way, or you could try to violate the sequencing constraints in a dynamic way. So we'll first look at static way. So before we move on to that, here are two examples of two different pieces of code that use the methods of the class file ADT. On the left hand side is the CFG corresponding to one piece of code that uses methods in a particular way. On the right hand side there's a CFG corresponding to another piece of code that uses a method in another particular way. So let's focus on the CFG in the left hand side. At node 1 it calls the method openF, which opens the file F. At node 2 it writes data onto that file. At node 3 it goes into a loop where it repeatedly writes data onto the file several times, and then when it comes out it closes the file. This is the control flow graph corresponding to some code that uses these methods. I have again abstracted out and given you only the details of the CFG as relevant to this lecture. In between it could do several other operations. We have not depicted that in the CFG, right? So here is a CFG of another graph that uses the same methods from the class file ADT. Always it begins with open. Please remember that unless it begins with open, if it directly does a write or a close, it will violate the sequencing, one of the sequencing constraints. So it always begins with open, and then like the earlier code, it can do one write and close the file, or it can write and close several times in a loop, which is this right hand side 3, 5, 7, right, and get back. So now what we will do is that if this is the first CFG of some code, this is the second CFG of some other code, we will take these sequencing constraints and see whether these two pieces of code or CFGs that uses these methods, do they satisfy these sequencing constraints or do they violate the sequencing constraints? As I told you, this can be done in two ways, statically or dynamically. What I mean by statically? Statically means I don't execute the code. I consider the CFG as a graph and then try to see if sequencing constraints are violated. Typically, static analysis is not considered a part of testing, but I'll just tell you for the sake of completeness here. So how does static testing of sequence constraints of CFG work? It proceeds by checking one constraint after the other. Go back to the constraint slide. There were 4 constraints. First says open must be executed before write. Second says open must be executed before close. Third says write cannot be executed after a close unless there is an open in between. Fourth says that write should be executed before every close. Right? So for constraint 1, we check if there is a path from an open to a write. Where is open here? I am focusing only on the CFG on the left hand side for the purposes of this. Open is at node 1. There are writes at node 2 and node 5. So for the first constraint, I check whether there is a path from the open at node 1 to writes at node 2 and node 5. It so happens that there are. So we are doing fine as far as the first sequencing constraint is concerned. For the second one, similarly, you check whether there is a path from an open open at node 1 to the close at node 6. It so happens that there are, if you see 1, 2, 4, 6 is one path, 1, 2, 3, 4 is one path, 1, 2, 3, 5, 3, 4, 6 is one path. So there are paths. So as far as the second requirement, open must be executed before every close, I'm still doing fine. For constraints 3 and 4, I have to check if there is a path from node 6 to any of the nodes with a write, and if there is a path from open to close without a write in between. So there is a path from node 6 which is a close to any of the write. So if you see, there is a write that happens at node 5 before close, there is a write that happens at node 2 before the close, but if you see, there is a path from open at node 1 to close at node 6 without a write. Which is that path? That path goes through node 3. I open the file, I go to node 3, I don't do anything. Specifically, I don't do a write. Then I go to 4, I skip the loops, that is, and then I close. So I have opened the file and closed the file without doing a write in between. So which is the constraint that it violates? It violates the fourth constraint. It violates the constraint that the write should have been executed before a close. That's what is given here. Path 1, 3, 4, 6 violates the constraint. Please note that in this slide, all the constraints we are reasoning about with reference to this CFG, the CFG on the left hand side. The CFG example on the right hand side, I will use it when I do dynamic testing. Now, when it comes to dynamic testing, my goal is somehow to be able to find paths that violate sequencing constraints. So I write test requirements or TRs that tell you what to cover. So I'll say cover first sequencing constraint, second sequencing constraint, and so on for each of the sequencing constraint. And my goal is to find test paths that violate the satisfaction of the sequencing constraint, right? So if I consider dynamic testing and I go back to the first CFG, the path 1, 3, 4, 6, which potentially violated constraint 4, could not be realistic. If you remember, I told you whenever we look at control flow graphs, it many times may not be feasible to write a path that altogether skips a loop. 1, 3, 4, 6 in this CFG is such a path. It could be the case that the loop was a do-while loop and you're forced to execute one iteration of the loop at least to be able to do. So suppose you have that, then when you do dynamic testing, you will know about it because you actually execute the software, and then path 1, 3, 4, 6 might not be an actual violation of a sequencing constraint. But in static testing, you will flag it as a potential violation of the fourth sequencing constraint. But when you do dynamic testing, you will know whether it was actually a false positive or it is a genuine violation of a sequencing constraint. It will be a false positive if the code for the CFG forces you to enter the loop. It will not be a genuine violation, it would be a false positive. But if the code allows you to skip the loop, then it will be a genuine violation of the fourth constraint. You can find out this through dynamic testing. So the other thing that we do in dynamic testing, as I told you, is to write test requirements that violate the sequencing constraint and apply these test requirements to all the programs that use the methods from this class. Right? Typically, for large programs, it's actually quite difficult to write all the sequencing constraints, to write the TRs for each of these sequencing constraints, and to be able to get test paths. And it's usually undecidable, but we won't really worry about proving which are the programs for which it is decidable or undecidable. The idea is to be able to understand how it is done. So what I do now is I write test requirements for all the constraints. There's one TR for every constraint. There were 4 constraints, so there are 4 TRs. First one says that you cover every path from the initial node to every node that contains a write such that the path does not go through an open. This will violate the first constraint, right? So it says you cover every path that goes through a write but without going through an open. Let's go back and see what constraint 1 said. Open must be executed before every write. Suppose you are able to find a path that will meet this TR, then you have violated the first constraint. right? Similarly for second constraint says that before a close, a file must be open. So the test requirement to violate the second constraint will say you cover every path from the start node to every node that contains a close command called to the close method such that the path does not go through an open method. Suppose you find a test path, you have successfully found a test path that violates the second constraint. Similarly, for the third sequencing constraint, your TR says you cover every path from every node that contains a close to the node that contains a write, which means a write has happened after a close. Fourth TR says cover every path from a node that contains an open to a close without going through a write. I've basically written the same sequencing constraints, but in terms of coverage criteria that violate the sequencing constraints. I hope this is clear. So if I do dynamic testing, I will find that again the fourth constraint is violated. So in this case, we will look at the second CFG, this one. How is the fourth constraint violated? There is this path, right? 1, 3, 5, 6, 3, which tries to write and not close a file. It tries to write once, goes back to 3, tries to write once more and doesn't close a file, and after that only closes a file. So through dynamic testing, I will be able to find out whether there is a violation of the sequencing constraint or not. So in summary, what do? I identify sequencing constraints if they have not been documented by designers. What is my test requirement? I write test paths that try to cover the test cases in such a way that if my test path is found, then one of the sequencing constraints is violated. So I write one test coverage criteria for violating each of the sequencing constraints. And suppose I identify in a test path that achieves this coverage criteria, then I have successfully found a path in the graph that violates a sequencing constraint, which leads to an error, right? Sequencing constraints can be of two types. The first type is plain example like we saw for the queue example or the file open, file close example. Sometimes you can have sequencing constraints that need to count the numbers that happened in the past, the number of certain kinds of operations that happened in the past. Those are called stateful sequencing constraints. And in the next module, we'll introduce finite state machines or finite state automata with which we can work to model state behavior related sequencing constraints. Thank you.